I have made several improvements on the interferometer. I have this good oscillator at, as it turns out now, 26.9 dBm. It has been 30 dBm before, but maybe I've changed something that I have forgotten. After that, there is the hybrid and the mixer, taking half the power and mixes it with the signal from the other local oscillator. I have added a 40 dB amplifier here with an offset potentiometer, so I can set at what level from the mixer the frequency control here is working well. Another thing is that I had before a 3 dB hybrid here. I have now a -8 dB coupler. This means that the signal, which is here 21.9 dBm, when it reaches the mixer for the PLL, it's only 13.6 dBm. But that doesn't really matter, it will lock anyway. But when it reaches the hybrid, where the two signals are compared and balanced to 0, the level is now higher. It is 20.8 dBm. So 20.8 dBm. After the hybrid, I have 17.4. If I disconnect one or the other of the signals, if both are present, I have almost 0 here. Means very low signal level. Then there is a band pass filter. It attenuates a little bit, but much less than before, because I have made a different and better filter. So it brings down the level by 0.3 dB only now. Then there is the impedance match. It attenuates by 0.5 dB. And at this point, the signal level is 16.5 dBm. That is without this notch filter. With the notch filter, it is 0.8 dB lower. I have replaced, or I have added one more LNA, so the noise figure here is now 1.6 dB only. This means that the noise floor is at -172.4, and that means that with respect to the carrier it is -188.9, and with the notch it is -188.1. And here you have what all of it looks like. Many boxes. On the Linrad screen I see a very interesting structure. At the notch frequency here, the noise is very low. And I can calibrate, but that's not so easy anymore, because the gain has become much higher. The signal is at 0.5 dBm, and you can see on the schematic diagram where I'm looking. The reference is at -69.5. That is 70 decibels below, just on the limit where the accuracy of this instrument starts to become questionable. And it's the level from this from this signal generator. When I look on the Linrad screen, the signal 50 kilohertz offset is 70 decibels below the carrier, and I have to calibrate properly. So 74.22 is the calibration I have to feed in. 74.22. And now I read, as I should, I hope, minus 69.98. That is close enough to 70 dB. So I switch off the signal generator. And here is the noise floor. The bandwidth is fairly accurately 1 kilohertz. And the noise floor I see, well, is minus 150.4. And that is dB below the carrier in 1 kilohertz bandwidth. Means 180.4 dBc per hertz. And now I step in the attenuator, 10 dB, where I know that the impedance is very accurately the same. And the noise is much lower. (156.8). I had 150, and now I have this bug. Now I have 156.8, so that's 6 dB below. It means, well, I see the spectrum is different now, and I can see on the oscilloscope balancing is no longer perfect, so I have to repeat this. Tuning the amplitude. This is the phase balance, and here is the amplitude balance. And phase balance again, and amplitude. Here the signal is small, and I again connect no attenuation. And now I have a better reading, I think. Minus 155.1 with a spectrum like this. And here is the cancellation of the two signals. And like, this is not so easy anymore. Like that. And then once again, minus 155.5. And now I insert the 10 dB attenuator. And the noise doesn't change much. It goes from 155.5, and I have to write that down because my short-time memory is not so good anymore. And to minus 156.99, that's minus 157. The noise floor I have seen minus 157 in 1 kilohertz. That's minus 187 in 1 hertz. That's pretty close to the expected minus 188.1. Since the signal, the noise floor plus the sideband noise is 1.5 dB higher than minus 157, it means the increase of adding the sideband noise is 1.41 times. So the sideband noise is 0.41 times the power of minus 157. That's 3.9 dB. So the noise I find is minus 157 minus 3.9. That is minus 160.9 in 1 kilohertz bandwidth. And that is minus 190.9 dBc per hertz. And this is the sideband noise of my good oscillator. The other oscillator is not at all as good as I have been thinking, and I will demonstrate that by removing the notch filter. This thing that will increase the signal level by 0.8 dB, but it will make a dramatic change on the noise floor at the notch frequency. The signal has increased, of course, since I removed some attenuation. It is now 0.85 dB, 1.3 dBm. So I need to set the weak signal at minus 68.7, like this. And then, of course, I have to change the calibration. Well, it was 68.7. I think maybe I should increase a little. No, 68.8, 0.1 dB, that's accurate enough. And here, as expected, the signal is 0.8 decibels stronger, so I have to recalibrate. Like this. Now the noise floor is at minus 151.9, still 50 kilohertz offset, but without the notch filter. And I cut in the 10 dB attenuator, and you can see the noise floor is now much lower, so I don't have to take it into account. The sideband noise of this oscillator is minus 151.8, make it minus 152. That means minus 182 dBc per hertz. And that's not far from what I have found before. But what I see now is there is much more noise at larger frequency separations. And as you can see here, the noise is going out. That's because the balance has degraded. I have to keep this thing very small by tuning these adjustments that I have. Like this. And it drifts with time, so this is not so easy. But you can see on the scale here that on the color that the noise has gone down a little. I have now connected this unit to my notch filter. That is a selective load, the notch and more notches, and then into the low noise amplifier with 1.4, I don't remember, but with a very low noise figure. It's a PSA 45043, and then I added a low pass filters so I can see easier on the oscilloscope, because the overtones at 20 megahertz make it look more difficult. And then there is another low noise amplifier into the passives. And what I see on the screen is this. It's the same thing. Something went wrong with this oscillator sometime. I don't know what the error is, but it's obvious that the sideband noise is much higher at large frequency separations. And of course, close to the carrier, the noise goes down because of the notch, but not to the extent that you see here. So something causes wideband noise. And that is a separate study. I think I will end here with this demonstration of the interferometric measurements. What I will want to do is to make one more really good oscillator like this one, and tend to run both of them on the interferometer. And in order to look at the noise at very close separations, because looking at 50 kilohertz, then the notch is perfect, as you can see here. But I cannot look at, let's say, 50 hertz or 10 hertz frequency separation, and that's the kind of ranges that is important in commercial applications of oscillators, as I have understood. That's for time measurement. And I have no idea how this thing would perform at close range. That's beyond what I have been able to study so far. This is the other oscillator, this one. It has 6 decibels more power, and it has a normal look here, it seems. At the center we have the effects of the notch. I now connect this one instead. And it has this odd feature here. And the noise is about 10 decibels higher, even more. So performance here is 16 dB worse for this unit as compared to that one. So I need to find the error here, or maybe make a new one.